we've been talking about apparent magnitudes of stars. Apparent magnitude of stars is how bright the star appears in the sky. It really has nothing to do with how bright the star really is, because you could have stars that are different distances and different brightnesses. Early astronomers used to think all stars were like the sun, and so the dimmer ones were farther away. But that's not necessarily the case, because the stars themselves actually have different wattages. And so we want to include that effect. Imagine we have someone looking out here and they see two light bulbs and they're equal distance away. One light bulb is a higher wattage light bulb than the other, so it looks brighter. So this one looks brighter than that one. On the other hand, what if these light bulbs are different distances away? Now the bright one might look the same brightness as the dim one, or it might even look dimmer than the dim one if it's far enough away. And so now we're going to have a different sort of thing. They're going to look different brightnesses, different magnitudes, or it could be that they're the same brightness, and in fact, the closer one does look brighter. But there's a lot of other things that come in here. So this is where we need to define something that we call the absolute magnitude. That's going to be a reference number that tells us precisely how bright a star really is, intrinsically. Intrinsic meaning in and of itself, not how bright it looks, but how bright it really is. So the absolute magnitude, we need a reference. So what we do is we imagine if we put a star 10 parsecs away, how bright would it look? So the absolute magnitude is the magnitude the star would be at a distance of 10 parsecs. So there's an equation for that. The absolute magnitude, and we use the capital M to be absolute magnitude, and that's going to be the apparent magnitude of the star plus 5 minus 5 times the log of the distance. And so this would be the absolute magnitude of the star. Now, that other equation there, hang on, I'm going to get back to that in a little bit. Okay, but the absolute magnitude of a star. Okay, so let's look at our chart again here. And if we look at our chart, let's consider these two stars right here, Beta Aurigui and Epsilon Canis Majoris. They are almost the same brightness. This star is a little bit dimmer than that star, okay, but they're way different distances. Beta Aurigui, which is just a tiny bit dimmer, this is a much smaller parallax, so that means it's closer. Remember that distance is 1 divided by parallax. And so that means it's a much closer star, but it's only a tiny bit, it's actually a tiny bit dimmer than the other star. So what we want to know is, what's the actual difference in these stars? Okay. So we've got Beta Aurigui, okay, and Epsilon Canis Majoris. Okay, so Beta Aurigui had a parallax of 0.40, okay, and it had an apparent magnitude of 1.90. Epsilon Canis Majoris had a parallax of 0.008 and an apparent magnitude of 1.5. Now, if I ask which one's brighter, this one's brighter. If I ask how many times brighter, remember times brighter, that would be, the brightness of one divided by the brightness of the other. That's 2.512 raised the difference in magnitudes. That's 2.512 raised to the 0.4 power, because there's a difference of 0.4. Now, I didn't ask you to divide the magnitudes because we don't know what those brightnesses are. The math of finding that is way beyond the level of this class. But we can do 2.512 raised to the 0.4 power. And so we find that there's a difference of about 1.45 times difference in apparent brightness. So that means that this star, Epsilon Canis Majoris, looks like it's just under 1.5 times brighter than the other star. Now that's what it looks like. What about absolute magnitudes? So what is the absolute magnitudes of these stars right here? So now let's look at to find absolute magnitudes. We know that M equals parent magnitude plus 5 minus 5 times the log of the distance. So what we have to do is find the distance. Well, distance is 1 over parallax. So distance is going to be 1 over 0.4. So the distance of Beta Aurigui, so that's going to be 1 over 0.4. So that's going to be equal to 2.5 parsecs. Okay. Now, for the other star over here, the distance is 1 over 0.008. And so all we got to do is plug that in. That's 125 parsecs. So vastly farther away. So absolute magnitude. If I want to find the absolute magnitude of these stars, then the absolute magnitude of Beta Aurigui up here is going to be equal to 1.9. So for Beta Aurigui, absolute magnitude is apparent magnitude plus 5 minus 5 log d. So this is my Beta Aurigui star. And so from the numbers that we had before, that's going to be equal to 1.9 plus 5 minus 5 times the log of 2.5. So this has to be in parsecs. Well, how do you find the log of 2.5? Well, guess what? There's a button on the calculator that does that. Okay, so just log of 2.5 is 0.398. So absolute magnitude is 1.9 plus 5 minus 5 times 0.398. Okay. Now, you have to be careful how you enter this in the calculator so that you don't accidentally take the log of 5 instead of the log of 2.5, because some calculators take log of what comes after the log button, and some calculators take the log of what's already on the screen when you hit the log button. So you got to look and see how does your calculator do it, because every calculator is different. So look at the instructions for your calculator. So, but if you do this correctly, then the absolute magnitude of that star, okay, the absolute magnitude of the star is going to be equal to okay, 9 plus 5 minus 5 times 4.91. So the absolute magnitude of Beta Aurigui is going to be 4.91. Okay, now let's find the absolute magnitude of the other star. Okay, so let me erase all that. Now, if you don't get 4.91 when you did that, go back and figure out what you need to do. Okay, figure out how to use your calculator. So that's the absolute magnitude of that star. Now, the other star was Epsilon Canis Majoris. Okay, and so we want to do the same thing. Absolute magnitude is apparent magnitude plus 5 minus 5 log d. So that's going to be equal to apparent magnitude 1.5 plus 5 minus 5 times the log of 125. Okay, and so now we want to do that. Okay, log of 125 is 2.1. So this means the absolute magnitude is 1.5 plus 5 minus 5 times 2.1. So the absolute magnitude is -4. Now, remember I said the Epsilon Canis Majoris looked like it was a tiny bit brighter. Okay, so we calculated that. We calculated it, and it was only just a little bit brighter. How many times brighter? Okay, but now we find that this is really a super bright star. It has an absolute magnitude that is enormous bright compared to that absolute magnitude that's pretty dim. So what is the actual intrinsic difference? If I look at this and say, okay, how many times brighter is it really? Not how much does it look like, but how much is it intrinsically different? So what we would do is we do the same thing. So we'd look for the actual luminosity. This is like the output, the power, the wattage. It turns out to be the same thing, 2.512 raised to the difference in absolute magnitude. So not apparent magnitude, but now absolute magnitude. And so that's going to be 2.512. Well, the difference, 4.91 minus a negative 0.4, is going to be 8.91. Now, you don't subtract the other way, because if you subtract the other way, you get a negative number. You cannot have a negative number in the exponent, so that determines which order you subtract. And so this now tells us that the star is about 3,670 times brighter. So before, we found that the apparent brightness was only a few times brighter, but in reality, this is almost 4,000 times brighter star. That means if you put that star where the sun is, it would bake Earth. And so be worse than West Texas in the summertime. Okay. So this gives us the idea of absolute magnitudes and how we're going to use them. So now the question is, why do different stars have such ridiculously huge differences in absolute magnitudes? We're not talking just slight differences. So that's why I said it's a little bit naive to say the stars are like suns, because they're way different. Many of them are way, way, way brighter than the sun, and many are way, way, way dimmer than the sun. And so we want to know why. Why are these stars different? What's really different about them? And so how does this tell us how one star differs from another star? Now, to understand that, we have to understand light, because that's really all that we're measuring when we are measuring things in the sky. I mean, you look at a star, you're measuring the light of the star. And so if you understand how light works, you can understand how stars work, because you're understanding what you're actually measuring. And so that's the idea here. So our next topic of study is going to be going back to the chapter about light. So we're going to start now discussing the physics of light in order to understand how to apply that to figure out how stars work.